Hi class, welcome back to the lectures on quantum mechanics, and this is the third lecture for chapter 5. And again, our main reference for this lecture is Introduction to Quantum Mechanics by David J. Griffiths. And again, I'd like to request you to get a hold of this book. This is highly recommended for you. This will really help you in guiding in the lectures. For this lecture, we will study about solids. So we've studied about atoms, we've studied about how the electrons are arranged in an atom, but in this case, we're taking the atoms into a group and we're looking at solids and how the electrons behave in solids. So in solids, in atoms you have electrons revolving around the atom, and you have there the outermost electrons of the atom, and these valence electrons are loosely attached from the atom. So when they're arranged in a solid, the outermost electrons or the valence electrons are detached from the atom and they roam around throughout the material, and they're no longer subject to the Coulomb field of the nucleus of the atom. But if the atom is, of course, detached from, if an atom is detached from other atoms, put it in space, of course the valence electrons will just have no choice but just to revolve around the atom. But if they are lumped into like a solid, these valence electrons, the outermost electrons of the atoms, they just roam around. They change from one atom to another in the entire crystal lattice of the solid. So we consider these electrons to be like a free electron gas. So if we consider an object to be a rectangular solid, you have their dimensions Lx, Ly, and Lz, and we imagine that an electron inside it experiences the potential 0 if it's inside the solid, so 0 if it's 0 between, if the particle is between 0 and Lx, 0 and Ly, and 0 and Lz. Otherwise, when it's out of the solid, the potential is infinity, meaning that the electron just stays inside the solid. So we can get the Schrodinger's equation for that. So we have here the Schrödinger equation, which has no potential because the potential is 0 inside. So we don't, because the solid cannot exist outside, the psi or the wave function outside is 0. So in Cartesian coordinates or rectangular coordinates, you can separate the psi into single coordinate product of single coordinate functions here, just like what we did in the previous chapter. So we can then separate the differential equation into 3 here for x, for y, and for z, and then we have the total energy to be the sum of the energy associated with the x plus the one associated with the y and the other associated with the z, because while the wave functions uh, are can be multiplied, the energies associated with that can be added. So we can let kx to be this one, and also that one, and that one. So you have kx equal to square root of 2m e of x all over h bar. Similarly for ky, where the energy is ey, and for the kz, where the energy is ez. So we can obtain the solutions as well, if we go back, these are just each of these are just particle in a square well. This one here, so you have 3 particles in an infinite square well. So you can obtain the solution for each one. You will have x would be an amplitude ax sine kx of kx times x plus bx cosine kx times x. So with the y and the z. So the boundary conditions require that at x of 0, y of 0, and c of 0, the wave function is 0, and so of course your b, y, and bz are 0, and your x lx, y lx, and z lz is also 0. They are also 0. So therefore, the only way that you can have that boundary condition is for your k x lx to be some integer times pi. So with ky ly and kz lc, so you will have this one in order for your wave functions to be 0 at the boundaries. So here your ny and nx, ny, and nz can have the values can have the integral values, and so why not start 0? It cannot start at 0 because the energy would be 0 for an infinite square well. So we need a lowermost energy at n equals 1. So the ground state would be the ground state psi would have nx equals 1, ny equals 1, and nz equals 1. That's the ground state, not 1 0 0 or anything. It doesn't start with 0, so it starts with n equal to 1. So this is the ground state. The ground state. So by multiplying the normalized wave functions, we can have the wave functions, the product of the 3 wave functions, to be here, this one. So you only have sine because the b's, the coefficient b's are 0 as given by the boundary conditions. So you will have this. You have 3 sine terms, and then you have square root of 2 over lx times square root of 2 over square root of 2 over lx times square root of 2 over ly times square root of 2 over lz. And of course, as you have derived in chapter 2, the energies are for each particle in an infinite square, you have h bar square pi square n square over 2m times the width of the well. So in this case, you can for the solid, you have En to be h bar square pi square over 2m times the sum of n square over nx square over 2lx square plus ny square over 2ly square plus nz square over 2lz square. And this is equal to, of course, h square k square over 2m, where k is the magnitude of the wave vector k here, this one here. So if you could imagine that in a three-dimensional space with kx as the axis, ky and kz, and the coordinates in kx is divided in such a way that the first k would be pi over lx, and the other one, and the next one is 2 pi over l. So for each kx, ky and kz, if you draw walls or plane in each values of kx and also each values in ky, each values in kz. By the way, this is kz, not ky. So when you draw the planes, you will enclose a region where in this region is enclosed a particle in that particular state. Each block in the grid, as you can see, you have a block that occupies a volume in K space. The volume is, of course, Lx, Ly, Lz. Here, if we magnify it, so this is Lx, this is Ly, this is Lx, and this is Lz. So you have this. The shaded region indicates there a block of a single state or a single particle in a particular state in K space. Now suppose there are n atoms in the solids. Of course, this n is very large, in the order of Avogadro's number, and each of the atom contributes q free electrons. So for each atom you have q electrons, not just one. You can have 2 or 3 or more. So again, if the electrons were bosons or distinguishable particles, they will fall to the ground state. All the electrons will fall to the ground state. But since electrons are identical fermions, they somehow are distributed uniformly throughout the volume. But again, as fermions, as identical fermions, only 2 electrons can occupy the same state. So only one spin up and one spin down electron can occupy a given state. Thus, only 2 electrons can be in one of the box in K space at the same time. So if you look at 1 octant of the space, the K space, and in that octant you have n atoms, then you will have nq electrons in that octant. But if you have nq electrons, since a block can only contain at most 2, then on the average you have to divide by 2, because that's the number of blocks that you have in that octant, and each block has volume equal to pi cube over v. And then of course this is 1 octant, so you have 1/8 here, and the volume of the sphere, where the radius is just set to kf. So you will have your kf. You can get the radius of that solid to be 3 rho pi square to the 1/3. So here you have by the way, your rho is just the density of the electrons in that volume, so you have nq over v. The boundary that is occupied in the boundary of the volume that is occupied by the electrons in the solids is called the Fermi surface. That's why you have a F in the kf. This is the Fermi radius of the solid. So now you will have, since your energy is as you have here, your energy is h bar square k square over 2m. So your energy of that particular octant in the solid is equal to this expression, and this is your k, or the Fermi radius. By the way, this is the octant that I was talking about, so it's just 1/8 of the sphere. The volume of the octant is 1/8 of 4/3 pi k cube. So when you just want to get want to look at the surface is just, of course, the derivative of the volume. And if you have a surface and if the surface area increases, it encloses, or if the radius k increases, it will increase the volume of the sphere. And the increase in the volume is just the derivative of the volume. So here is just, you can cancel 8 and 4. This is 1/2, and the derivative of the volume will just be pi k squared. So this is the increase in the volume as the radius of the volume increases. So the number of electron states in the shell would then have a change of, so you have 2, because there can be 2 electrons in one state. And then you have this one here, the change in the volume, and this one is the volume of every state. So this is now the total number of electron states that can be changed as the, or that can be added or maybe subtracted as the volume or as the radius k changes. But each of these state carries an energy equal to h bar square k square over 2m. So you have to multiply each of them by this energy, and so your total energy change will be this. This was your number of electron states, and this is the energy in that state. This is the change in the volume, or change in the number of electron states, this one here. And since they are located in the outermost surface with energy, or with k equal to k, or kf equal to k, then the energy in that particular region would be h bar square k over 2m. And so if you want to get the total energy, you just have to get the integral of dE, on integral of the left side and then on the right side. So you will have E total to be this one here. So everything will be constant except for k, and then you will have of course h bar square times b over 2 pi square over m, and then you have here the kf, by the way, is equal to, kf is 3 rho pi to the pi square to the 1/3. So you can change this kf here with that, and then finally you will be able to get this one here. This energy is analogous to the internal thermal energy U of an ordinary gas, but here you have a gas of electrons, so you have here this result. It's a quantum mechanical result. In particular, this energy exerts pressure on the walls of the solid. So if the box expands by an amount dV, the total energy decreases by some amount, and this is just equal to here. So you just since in gases you have this one here, the work is just the pressure times the if the volume of the gas expands by volume dV, you do a work by an amount P times dV. So in this case, if you get the derivative with respect to V, then you will also get the pressure. So this is this one. So as an analogy, you can get the P to be equal to this expression. So this is just 2/3 E total over V. So this is also the quantum mechanical pressure of an electron gas in the solid. That pressure earlier that we have calculated explains why a cold solid does not collapse. And by the way, this is sometimes called degeneracy pressure. Also sometimes they're called exclusion pressure. This pressure stabilizes the solid. And this is, by the way, this pressure is not caused by electron repulsion, but this is caused by the spin of the fermions. So now we can go to the band structure, and here we improve our model by including the forces exerted on the electrons by the regularly spaced positively charged. So you have, because in an atom you have a nucleus that is positively charged, and we set that nucleus of an atom. Of course, you're not dealing with a single atom here, you're dealing with an array of atoms, and they are regularly spaced in a solid, and then that will actually have an effect on the electron gas. So that potential will actually give you a periodic one, because they're regularly spaced, and so we can create a model for that. And the one-dimensional model that we can have is the Dirac Cone. here you have, for example, these are the regularly spaced nuclei, the potential of the regularly spaced positive charge. So if you have an electron here, it will experience a potential which is the same as if it is as when it is put here or here or here. So the difference is just the locations of the region. So for example, the electron will experience the same thing here as when it is put here or even here, but the locations are different. But the locations are you can predict the locations by just an increment of a. So you have here 0 to a, then here a to 2a, and then from here from 2a to 3a. So it's just regular. So you have the difference here, a, and here it's also a. Also here it's also a. This is a one-dimensional Dirac Cone consisting of evenly spaced delta function wells. So if you have a particle in one region, as I've said earlier, they experience the same potential as it is in another location because of the regular spacing of the nuclei. So your potential at some location Vx would just be the same at x plus a, or even x plus 2a, or x plus 3a. So this would just be the same as Vx at Vx plus Na, where a is an integer, or Ka for example, depends. So here we are actually doing the Blocks theorem that tells us the solution to the Schrödinger equation here, where of course the potential has the behavior of this one here. And so for such a potential, you can have your psi also to satisfy this behavior as well. For some k, so your wave function x plus a will just be that function, and then you have e to the ika, which is behaving periodically inside the solid. This is just proof that your alpha is equal to this one. I mean lambda, sorry. Your lambda is just equal to that one for here. So anyway, the proof is not important, but for as long as we know it, that the wave function satisfy this, it's the proof may be ignored, but of course you have to know the proof as well. So that's the behavior of the wave function. Well, the potential has the behavior of when you when you have a when you add a regular spacing, the potential remains the same. So of course, your wave function, so that's the probability. So your wave function here also follows this condition, because anything would be the same, because anything would be the same in the regions 0 to A, or A to 2A, or 2A to A3, to 3A, and so on. No real solid goes on forever. So the periodicity of the potential will be spoiled. So we're going to apply Bloch's theorem such that it will seem that the solid goes on forever. But of course, again, there's no real solid that goes on forever. But no matter how small the solid is, as you can see in your naked eye, it still contains a lot of, millions of atoms in that particular solid, even how small it is, as you can see it in your naked eye. So here we have the Dirac Cone. You connect the beginning and the end such that it will form like this. You draw, it will form like this one here. So it will seem like it will go on forever. So as for any object visible to the naked eye, each of these objects will contain Avogadro's number of atoms is so many, 10 to the 23 of them. And it is hardly imaginable that the edge effects can significantly influence the behavior of the electrons deep inside. So within the object, the electron still feels so free. So your wave function now has this behavior with Bloch's theorem. And so with the above prescription, our wave function now follows this one, behaves this one, like that. So of course, since this one here and this one are equal, then this must be equal to 1. And of course, for this to be equal to 1, your nka must be equal to 2 pi n, and so that your k will have to be of that form where n is equal to 0, 1, positive 1, positive negative 1, positive negative 2, and so on. So k is a real number here, a real number, not an imaginary one. So in this case, we only need to know, by Blocks theorem, we only need to know we only need to solve the Schrodinger equation in a cell, and then we can apply for we can do recursive application of the equation and then generate the solution everywhere in the system, because you have nuclei that are regularly spaced. Now, for example, if you have a potential consisting of a long string of delta function wells, which are the Dirac Cone, so your potential will look like this. You have a summation of Dirac delta. The wells are the Dirac delta wells are the teeth of the cones, and it represents the electrical attraction of the nuclei in the lattice. And you must imagine that the end or the comb is wrapped around so that it will represent an endless comb, so that your nth well will actually appear at x is equal to negative a if you have a very long comb. Of course, this is not a realistic model, but this one will approximately give us this model give us the unending periodicity of the potential, or of the system, I mean. So for regions 0 to a, of course the potential, as you can see in the comb, is 0, but it has a barrier, a delta barrier on the boundaries. So again, for 0 to a, you have the solution. If you can just review your previous chapters. By the way, this will now be your differential equation between the two boundaries, or you can write it like this, but your k have to be square root of 2m over e all over h bar. So of course, if you go to another cell, it will be, since we have phi, sorry for that, since we have phi x equals e to the I k a x plus a, then we can also write, according to Bloch's theorem, we can also write this wave function to be this one here. So again, the wave function would have to be continuous at the boundary. So of course at x equal to 0 is a boundary where it's where the delta potential occurs. It's continuous there, so you can let x equal to 0, so you can say that your B is equal to this, that one. And also the wave functions continuity at the boundary is affected, as we have solved in the second chapter. It's affected by the delta function. So there's a discontinuity when you pass through a delta function, and the discontinuity, that's the derivative, so you have to get the derivative of the wave function, and so that discontinuity is given by this one here. This is the derivative of the wave function of the electron on the on one cell, and this one is on the other cell, this one here, the whole thing, I mean this one and this one, and the difference would have to be equal to 2m alpha over h bar 2 times b, where alpha here is the strength of the Dirac delta. So that will give you, this will give you this expression such that we can replace A, and we can cancel A and B such that we'll be able to get this expression. So you can do this algebraically. This result is very important because we can simplify it to some other terms. Like here we can set Z as Ka, and that we can actually write this function. We can write this cosine big Ka to Fz. This is cosine Z, and then you can set this as beta, and this one is sine Z over Z. So that by the way, here you can see that the beta is a dimensionless measure of strength of the delta function as well. That's of course that contains alpha here. That's the strength of the delta function. M is of course the mass of the electron, and A is the width of the cells, and then you have h bar square. So if you plot Fz for the case of beta equals 1, you can get the plot here. You can get the plot here. Look at this plot. You have here the values of Fz. The Fz should be within -1 to 1. The values of Fz should be within 1 to 1, because of the values of the cosine and sine. But here you have they have some extensions beyond that value. Look, here you have, these values are okay, these ones are also okay, these ones are also okay, this one here, here, and here. But there is a region where the values are not okay, and this region are called the gaps. Those are the band gaps of the solids. Depending on the material, depending on the electron content of the solid, they also have different band gaps. So in that figure, the Fz will have a value greater than 1 and even less than -1. So in that region, there's no hope of solving this equation here. So that's why there are gaps, and that gaps, or those gaps, are represented by this, the gaps here. So if this is a very wide gap, that means you need to have a lot of energy to cross that gap into the other energy level. So you need a lot of energy here if you want to go from this band to this band here, because this has greater energy compared to this one here. So if the gap is so wide, you need a lot of energy to go from one band to another. So for the first band, there are only n/2 positive energy states, and then for the succeeding bands you will have n states in higher energy bands. So as you can see in this figure, so I will just read the bullets here. Because of the Pauli exclusion principle, only 2 electrons can occupy a given spatial state. So if Q is equal to 1, they will just fill the negative energy, the negative energy half of the first band, and when Q is equal to 2, they will completely fill the first band, and for Q equals to 3, they will fill half of the second band, and so on. Now, if a band is entirely filled, it takes a relatively large energy to excite an electron. It has to jump across the forbidden zone, which is the gap, and if it needs a lot of energy, then such materials will have to be an insulator, because it needs more energy to jump from one energy band to a higher band. If, on the other hand, if a band is only partially filled, it takes very little energy to excite an electron, and such materials are typically conductors. So that's also the difference between conductors and insulators in a different perspective. But if you dope an insulator with few atoms of larger or smaller Q, this puts some extra electrons into the next higher band, or creates some holes in the previously filled one, allowing in either case for weak electric currents to flow. Such materials are called semiconductors. So we have three materials, insulators, which are completely filled bands, and then you have conductors, which are partially filled bands, so that you can transfer one electron from one band to another easily. And then you also have semiconductors, where the bands are doped with some atoms with significantly larger or smaller Q, and that will eventually give out some electrons to other bands. So they will provide holes or provide electrons that can transfer from one band to another. So you're making a semiconductor out of an insulator. So this is the end of this session. So I hope you will ask more questions during our Q&A session. So for now, that's the session for solids. So see you in the next meeting. I hope you can have now the list of your questions, so that in our Q&A we will go much faster and more smoothly with the discussion. I mean, the interaction. So see you next meeting.